After a brief introduction on oscillatory motion, particularly regarding the concept of stability, which is a necessary condition for oscillatory motion. Today we are going to start the first concept of this chapter. And actually this first concept is regarding the normal coordinates and the normal modes of vibration. This is actually a basic concept for the dealing with the theory of small oscillations. So for knowing the general theory of small oscillations, first of all, we will have to understand what are normal coordinates and normal modes of vibration. Actually, to develop the idea or concept of normal coordinates and normal modes of vibration, let us start with a particular physical problem, and that is actually the problem of two coupled oscillators. Actually, we will find out the equation of motion of two coupled oscillators, and we will try to find its solution, and then from that solution you will see that the concept of normal coordinates and normal modes of vibration come out. Okay. So before knowing the idea of normal coordinates and normal modes of vibration, we will start the problem to deal with the problem of two coupled oscillators. I hope you have a very clear-cut idea of linear harmonic oscillator, that is a spring mass system you have studied in your lower classes. But see this figure here. In fact, there are two figures here. This is, let us say, figure A, and this is figure B. You can see in this figure I have shown that this S1, S2, which I have shown by this shaded region, these are actually the rigid walls. When you say rigid walls, that means object of infinite mass. Okay? And two springs, you can see the figure, whose spring constants are equal, that is equal to K. These two springs are connected to these walls. That is, one of the ends of the spring is connected to the walls, and the another end of the spring is connected to a mass, let us say M. In fact, both of the spring is connected to the same mass, and that is M. Okay? And at the same time, you can see these two masses are also connected by a spring having some different spring constant, and that spring constant is K dashed. Okay? In figure A, we have shown that the system is in equilibrium. When you say that the system is in equilibrium, it means the net force acting on the two masses will be zero. For simplicity, we assume that when the masses are in equilibrium, then these springs are neither elongated nor compressed. It means no spring force will act on the two masses. Okay? We consider. And this dotted position actually represents the equilibrium position of the two masses. Okay? Now, the two masses are displaced from this equilibrium position slightly on this horizontal line. Let us say this is x-axis. This is just x-axis we treat. Okay? This first mass M is displaced by, let us say, x1 from its equilibrium position, and the second mass is displaced by x2 and released. You know, as the two masses are displaced from the equilibrium position, then the spring force will act on it, and that spring force will act like a restoring force, and the two masses will start oscillation about their equilibrium position. Okay? In fact, here, if the two masses are not connected to one another by the spring of a spring constant K dash, then this system will be just a linear harmonic oscillator, let us say like this and like this. Okay, and in that condition the frequency of oscillation is simply given by omega naught equal to root over k by m. Okay, when there is an independent oscillation or vibration of the masses. But as here in this present problem we have considered that the two masses are in fact connected by a spring of a spring constant k dashed. So the vibration of the two masses will be not independent from one another. So it is actually called the coupled oscillators. In fact, in this condition, when the springs are connected by a spring of force constant k dashed, the system oscillates with different frequencies. Okay, and our present interest is actually regarding the calculation of those frequencies. Okay, our aim is to calculate the frequencies with which the system will vibrate. Okay, now here since the two masses has been displaced by x1 and x2, so these x1 and x2 are treated like the generalized coordinates. So if you say that the first generalized coordinate is q1 which is equal to x1 and the second generalized coordinate is q2 and that is equal to x2. Since the two generalized coordinates will be used to discuss the motion of this system, so the system will have 2 degrees of freedom, because the number of independent variables needed to describe the system is called number of degree of freedom, and since here only two coordinates x1 and x2 are sufficient to deal with this motion, so this system will have 2 degrees of freedom. Okay, 2 degrees of freedom. Now actually in this problem, first of all we will set up the equation of motion of the system and then we will try to solve that very equation of motion. As you know, in classical mechanics there are two different approaches to solve a problem. First one is called Lagrangian approach and another is Hamiltonian approach. Actually here we will use the Lagrangian approach for solution of this problem. It means if your aim is to write down the equation of motion of this system, write the Lagrange equation for this system, okay, and then we will solve it. And as you know, the system is actually a conservative system because the spring force is a conservative force. So the Lagrange equations of motion are given like this. This is d dt del L by del qk dot minus del L by del qk equal to 0. You know that this qk are actually the generalized coordinates and qk dot these are actually the components of generalized velocities. Okay, but here as I have told you that in this case qk means what? Qk means q1 and q2 because there are 2 degrees of freedom, and q1 means x1 and q2 means x2. So the number of Lagrange equation for this system will be 2. Okay. So first Lagrange equation in terms of the coordinate x1 you can write this is d dt del L by del x1 dot minus del L del x1 equal to 0. And the second equation will be d dt del L by del x2 dot minus del L by del x2 equal to 0. So these are the two equations of motion. Okay. Here you know that this L is called the Lagrangian of the system, and how this Lagrangian is defined, Lagrangian is simply defined like T minus V, where T is kinetic energy of our system and V is its potential energy. Okay. So to solve the Lagrange equation which we have set up for this system, first of all we have to find the Lagrangian of this system. And to get the value of Lagrangian of this system, you can see this equation 3, we have to find the kinetic energy of the system and the potential energy of this very system. Okay? So kinetic energy T, as the springs are massless, so these three springs will have no kinetic energy because we have assumed that all the three springs are massless springs. So kinetic energy will be only in the two masses. Okay? Now the first mass has been displaced by x1. So at any moment t, its velocity will be what? Its velocity will be dx1 by dt, and that is written as x1 dot. So this x1 dot is the velocity of the first mass. So the kinetic energy of the first mass will be equal to half m x1 dot square. Okay. Similarly, the second mass has been displaced by x2 dot and x2, and so its velocity will be dx2 by dt, and that is equal to x2 dot. So kinetic energy of the second mass is half m x2 dot square. Okay. So this half m x1 dot square plus half m x2 dot square, this will be the kinetic energy of this system, that is the system of two coupled oscillators, because springs have no kinetic energy since their masses are 0. Okay. Now we will find the potential energy of this system. Since the oscillation in this case, you can see the figure, takes place on a horizontal surface. This is just a longitudinal oscillation, you can say. So the gravitational potential energy of the two masses will never change. And if we assume that this level on which the oscillation takes place is the reference level for the calculation of gravitational potential energy, then you can simply take that the gravitational potential energy of these two masses will be 0 or any other constant, either 0 or any other constant. Okay. So for simplicity, we consider that the gravitational potential energy of this system of these two masses are 0. So potential energy of the system means potential energy only of the springs. Only of the springs. Now you can see the first spring has been elongated by x1. So its potential energy will be half k x1 square. The second spring has been compressed by x2, and so its potential energy will be half k x2 square. Now you can see the spring connecting the two masses whose spring constant is actually k dashed. On the one hand, it is compressed by x1, and on the other hand it is elongated by x2. So the net change in length of the spring connecting the two masses, that is the spring of a spring constant k dashed, will be simply x1 minus x2. This will be actually either the compression or elongation of the spring having a spring constant k dashed connecting the two masses. So we will simply now add the potential energy of the three springs, and that will be actually the potential energy of the whole system. So potential energy of this system V is equal to what? You can see the potential energy will be simply the sum of the potential energy of the three springs. Okay. And the potential energy of first spring is half kx1 square, of the second spring it is half kx2 square, and the spring of a spring constant k dash connecting the two masses, its potential energy will be half k dashed x1 minus x2 whole square. Okay. So this is the potential energy of this system. Now you know the kinetic energy of this system and its potential energy. So let us substitute these values of T and V in equation 3, and then you will find the Lagrangian of this very system. So you can see Lagrangian L of this system will be what? This is T minus V. This is half m x1 dot square plus half m x2 dot square minus V, and V is this much. So this will be minus half k x1 square minus half k x2 square minus half k dash x1 minus x2 whole square. This is actually the Lagrangian of this two coupled oscillator system. Okay. Now after getting the value of Lagrangian, now we will find all the partial derivatives existing in the Lagrange equation of motion. You can see in equation 2a, the partial derivatives of L are del L by del x1 dot del L by del x1. In equation 2b, these are del L by del x2 dot and del L by del x2. So simply differentiating the Lagrangian L of this system partially with respect to x1 dot, x2 dot, x1 and x2, you can obtain the values of these partial derivatives. Okay. So see this equation number 4 and find all these partial derivatives. So partial derivative of L with respect to x1 dot. See this equation. In first term x1 dot is present. So this will be what? This will be half m 2x1 dot. 2 and 2 will cancel out, and so this will be simply mx1 dot. Okay. And when you will find and see the other terms. In other terms, x1 dot is not present and you are taking partial derivative. So when you will differentiate the rest terms, the result will be 0. So del L by del x1 dot will be simply equal to mx1 dot. Similarly, we will find del L by del x2 dot. See the second term, this will be differentiated and the derivative of all other terms will be 0. And this will be half m 2x2 dot, 2 will be cancelled, and so this will be mx2 dot. Okay. Now you can find del L by del x1. In first term, in second term, there is no x1 present, so its derivative will be 0. In the fourth term, it is also 0. Okay. But in the third term, you can see x1 is present. So this will be what? Minus half k 2x1. Again 2 and 2 will cancel. So this is minus half kx1. And now in the last term, again x1 is present. So when you will differentiate the last term with respect to x1, you will get minus k prime x1 minus x2. Okay, x1 minus x2. And similarly, you can find del L by del x2, and this will be equal to minus k x2 plus k prime x1 minus x2. Okay, this is a very simple differentiation, you can do it. Now, after getting the values of these partial derivatives, we will simply substitute these values in the Lagrange equation which we have written in this equation 2. You can see. Okay. So now let us substitute all these values. See here. The first equation is d dt and del L by del x1 dot. And you can see del L by del x1 dot we have obtained. This is mx1 dot. Okay. And minus del L by del x1. Del L by del x1. But see, del L by del x1 is this much. And when you will take minus, all these minus will become plus. So the second term will be what? This will be plus kx1 plus k prime x1 minus x2. And when you will differentiate this x1 dot with respect to t, that will be x1 double dot. So first term has been written as mx1 double dot. Okay. Similarly, we will substitute the value of del L by del x2 dot and del L by del x2 in this equation in this equation 2b, in this equation. Okay. And after substituting those values, you will get that the equation of motion is mx2 double dot plus kx2 and minus k prime x1 minus x2 equal to 0. Okay. Now you can see actually these are the second order differential equation, and these are actually called coupled equations. Why these are called coupled differential equation? You can see. In fact, in the first term, in the first equation, you can see the equation is in terms of the variable x1. Okay, but x2 is also present here. Similarly, in the second equation, the equation is in terms of x2, but x1 is also present. So these equations are called coupled differential equations. Okay. Actually, by the technique of uncoupling, these equations can be made uncoupled and then can be solved. Okay. So we will try the solution of this equation by trial method, and then we will find the exact solution of this equation. Okay. So after getting these two coupled equations by using the Lagrangian concept, now our aim is to solve these equations. Okay. As you know that these two equations are simultaneous linear differential equation with constant coefficients. Here the coefficients m, k and k dashed all are constant. Okay. So we will try the trial solution of these equations. Let us consider that the solution of this equation 5a is written as x1 equal to a1 e to the power I omega t. Okay. And the solution of second equation we take as x2 equal to a2 e to the power I omega t. Here actually these a1 and a2 are the arbitrary constants, and omega is actually the frequency of oscillation. Okay. So after substituting x1 equal to this much, x2 equal to this much, what will be our equations in 5? You can check. So for this you have to find the value of x1 double dot, which means d2x1 by dt square, and then you have to find x2 double dot, which means d2x2 by dt square. You can easily find these two values simply differentiating x1 and x2 with respect to t. And after getting the value of x1 dot double dot and x2 double dot, we will substitute these values in equation 5a and 5b. Okay. And instead of x1 and x2, we will substitute these two values. Okay. So you can do the algebra. I have shown it here, that after substituting those values, our equation will be minus m omega square a1 plus k a1 plus k dashed a1 minus a2 e to the power I omega t. E to the power I omega t will be just as a common factor. You can check it. I am not showing all the step of algebra. Okay. Now, as you know that this e to the power I omega t cannot be always 0. it may be 0 at a particular time, but it is 0 at all time, you can't say. So this e to the power I omega t may or may not be 0, but as the result in RHS is 0, so definitely the second factor must be always 0. Okay, so you can say that minus m omega square a1 plus ka1 plus k dashed a1 minus a2, this is equal to 0. Okay, now we will take this m as a common factor. Okay, m as a common factor. When you will and also we will take this a1 and a2 as common factor. So you can see in the first term a1 is present, in the second term a1 is present, in the third term also a1 is present. Okay, so now take m and a1 as a common factor. Then from in these three terms you can see in the first term there will be minus omega square. In second term a1 has been taken as a common factor and m also, but m is not present in second term, so you have to divide this k by m. Similarly, in k dashed a1 is a common factor and m will be divided here or 2. Okay, and in the last term k minus k dashed a2, that will be also minus k dashed over m into a2, and that is equal to 0. Okay, now here you can see that this k by m, you know, a square root of k by m is actually the natural frequency of oscillation of each oscillator when they oscillate independently. Independently, then that is equal to omega naught. Okay, and this k dashed over m square root, this is, I have assumed that this is equal to omega c. Okay, so after substituting these omega naught and omega c instead of this square root of k by m and square root of k prime by m in this equation, your result will be what? This will be omega naught square plus omega c square minus omega square a1 and minus omega c square a2 is equal to 0. Okay. Now similarly, we will substitute the value of x1, x2 and x2 double dot in this equation, equation number 5. Okay. And after substituting the values of x1, x2 and x2 double dot in this equation 5, what will be our result? You can see that this will be equal to minus m omega square a2 plus k a2 minus k dashed a1 minus a2, and e to the power I omega t will be just as a common factor. Okay, and that equal to 0. Okay, again you know that this e to the power I omega t may or may not be 0, so definitely the second factor will be 0, and this is minus m omega square a2 plus k a2 minus k prime a1 minus a2 equal to 0. Again you can see that a2 is present in the first term, in the second term and also in the third term. So all these three terms containing a2 are combined together, and we take m and a2 as a common factor, and the remaining terms will be minus omega square plus k by m plus k dashed by m and minus k dashed by m into a1. Again, instead of this k by m, we will write what? We will write actually this k dashed by m. This has been written first here, and this is actually omega c square. So this is minus omega c square a1. And instead of this k by m, we have written omega naught square. Instead of k dashed by m, we write omega c square, and this minus omega square is attached, and the common factor is a2. Okay. Now you can see that you can see these equations 7 and 8. Okay. Actually, these are linear equations in A1 and A2. According to theory of determinant, you can see that these equations 7 and 8 will have non-trivial solution or non-zero solution only when the determinant of the coefficients of A1 and A2 will be equal to 0. Okay? Only then these equations 7 and 8 will have non-zero solution. Okay? These equations will have non-zero solution. So let us substitute 0 for the determinant of coefficients of A1 and A2 in equations 7 and 8. The coefficient of A1 in equation 7 is what? This is omega naught square plus omega c square minus omega square. And the coefficient of A2 is minus omega c square. Okay? And here the coefficient of A1 is minus omega c square and that of A2 is omega naught square plus omega c square minus omega square. So let us put this determinant equal to 0 for the non-zero solution of those two equations. So you can see this is our determinant omega naught square plus omega c square minus omega c square minus omega c square omega naught square omega c square minus omega square equal to 0. Okay. Actually, this equation is called a secular equation. Now, let us solve this determinant. You can see, we will take the multiplication like this. Okay. You can solve this determinant. So, this will be omega naught square plus omega c square minus omega square times this much. So, this will be whole square. And minus omega c square minus omega c square, that will be minus omega c whole square, and so this is this much. Now we will simplify it on the basis of the formula a square minus b square. You know this is a plus b times a minus b. Okay. So this will be omega naught square plus omega c square minus omega square plus omega c. This is a plus b. And omega naught square plus omega c square minus omega square minus omega c square. Okay. So you can see in this condition the first factor is omega naught square plus 2 omega c square minus omega square, and here this omega c square and omega c square will cancel out. And the another factor is omega naught square minus omega square. Now, as the product of these two factors is 0, so we can equate every factor equal to 0. So, when you will take this equal to 0, that is omega naught square minus omega square equal to 0, then you can see our result will be omega square equal to omega naught square. It means omega will be equal to plus minus omega naught, and we write it for simplicity plus minus omega 1. This is the first frequency of vibration. So I have written it omega 1. Okay, we have assumed it. Now we will take the second factor equal to 0. So when you will equate to 0 omega naught square plus 2 omega c square minus omega square, then what will be omega square? That will be equal to omega naught square plus 2 omega c square. And so omega equal to plus minus root over omega naught square plus 2 omega c square. Okay. And we consider this frequency equal to omega 2. So omega 1 and omega 2 are actually the two frequencies of vibration of these two coupled oscillators. Okay. So in this as there are two frequencies of not only two, but there are four frequencies of vibration. First you have written actually plus omega 1 minus omega 1 plus omega 2 minus omega 2, although frequency is not negative, but the terms containing these frequencies may contain the exponential power as negative. So in this condition, the solution which we have assumed here, these in equation 6, these solutions now can be written in general form. As you know that these equations of motions are differential equation of second order, so definitely there should be the two terms or two arbitrary constant. Since these are coupled equations, so there will be actually 4 arbitrary constant in each solution. So you can see what are the general solution of these equations. The first general solution, we write x1 equal to a1 e to the power I omega 1t plus a1 dash e to the power minus I omega 1t. Here I have taken omega equal to minus omega 1. Okay, and the next term will be b1 e to the power I omega t plus b1 dash e to the power minus I omega 2t. So you can see there are 4 constants, a1, a1 dash, b1, b1 dash. Similarly, x2 can be written as a2 e to the power I omega 1t plus a2 dash e to the power minus I omega 1t plus b2 e to the power I omega t plus b2 dash e to the power minus I omega 2t. Okay. Actually here this a1, a1 dash, a2, a2 dash, b1, b1 dash, b2, b2 dash, all these a's and b's are arbitrary constants. Although they are arbitrary constant, but they are not completely independent of one another. You can see that these constants are not completely independent, but they depend on one another. And for this, if we consider the first value of omega, which is actually plus minus omega 1, and you have written plus minus omega 1 instead of plus minus omega naught. If we use this value of omega either in equation 7 or in equation 8, you can see this equation. Here you have to write omega equal to plus minus omega naught. Then you can establish the relation between a1 and a2. See here, when you will put omega equal to plus minus omega naught, after squaring that will be plus omega naught square. So this omega naught square and this omega naught square will cancel out, and the term will remain omega c square into a1. Omega c square into a1. Okay. And second term is minus omega c square a2, and that will be equal to 0. Now omega c square will be taken as a common factor, that will be removed, and from here you can see that this a1 minus a2 will be equal to 0, that is a1 will be equal to a2. And similarly you can say that b1 will be also equal to b2. When a1 is equal to a2, it means b1 is equal to b2. Okay. But when we take omega equal to plus minus omega naught, then this result comes out. So a1 and a2 are actually same in this case, and so you can say that they are not independent from one another. Okay. Again, when you take that this omega is equal to plus minus root over what? What is the another value? Plus minus root over omega naught square plus 2 omega c square. Omega naught square plus 2 omega c square. Let us substitute this in this equation. You can see. Instead of omega square, we will write this much. So omega naught square will be cancel out, and there will be 2 omega c square, and so omega c square minus 2 omega c square, this will be minus omega c square a1. And the second term is also minus omega c square a1, and that will be 0. So in this condition, you can see that A1 plus A2 is equal to 0, and therefore A1 will be equal to minus A2. A1 will be equal to minus A2. So you can see I have written it here that when omega is equal to plus minus omega 1, that is plus minus omega naught, then A1 is equal to A2, and when omega is plus minus omega 2, which is equal to plus minus this much, then A1 is equal to minus A2. Okay? And similarly, in this condition, when omega is equal to omega, so in this condition you can also say that this B1 will be equal to minus B2, and here this B1 will be equal to B2 when omega is omega 1, and when omega is omega 2, then B1 is equal to minus B2, A1 is equal to minus A2. Now we will use these results in this equation number 10. You can see when your frequency will be omega 1, then in first term in RHS of for equation x1 there is A1, and in x2 there is A2, but A1 is equal to A2 when omega is equal to omega 1. So instead of this A1, we will now write again A1. So you can see this is x1 equal to A1 e to the power I omega 1t, and in the term x2, this is again x2 equal to A1 e to the power I omega 1t. Both of these terms you can see is same. And similarly, the second term is A1 dashed e to the power minus I omega 1t, and so in the value of x2 this will be again A1 dashed e to the power minus I omega 1t. Okay? But here when omega is omega 2, then you know that A1 is equal to minus A2 and B1 is equal to minus B2. So in this condition, when here there was actually what? In this case, there was actually B1 dashed, and in the second case there was B2 dash. So B1 has been replaced by here minus B1, and B1 dashed, so here this B2 has been replaced by minus B1, and B2 dashed has been replaced here by minus B1 dashed. Okay? So these are the solution of those equations, two equations of motion. And you can see that among these solutions there are four unknown constants: A1, A1 dashed, B1, B1 dashed. Okay? Now actually as these equations you can see that x1, the values of x1 and x2 contain the factor e to the power plus minus I omega t. So this is just oscillatory function, and oscillatory function may be expressed either as a combination of the real and imaginary part of e to the power I omega t, or it can also be written in terms of only the real part of e to the power I theta. You know that e to the power I theta is equal to cos theta plus I sin theta. Okay? So if we write the values of x1 and x2 in terms of only the real part of e to the power I omega 1t and e to the power I omega 2t, then these two solutions in equation 12 can be written as x1 equal to a1 cos omega 1t plus phi 1 plus a2 cos omega 2t plus phi 2. And similarly x2 equal to a1 cos omega 1t plus phi 1 minus a2 cos omega 2t plus phi 2. You can see this equation 13 also contains four arbitrary constants, and these constants are a1, a2, phi 1 and phi 2. Okay? Since the equation of motion was actually second order differential equation, and actually the equations were two coupled equations. So there are four arbitrary constants. Okay, and actually we can find the values of these arbitrary constants by the method of variable separation, or you can say that by using the boundary conditions actually. And in fact, according to equation 13, you can see that x1 is just a superposition of two simple harmonic vibrations or motions of frequencies omega 1 and omega 2. And similarly, x2 is also a superposition of two simple harmonic terms having frequency omega 1 and omega 2. Okay, so we can easily say that this equation 13, and in this equation 13, each coordinate is a superposition of two simple harmonic motions of frequencies omega 1 equal to omega naught and omega 2 equal to root over omega naught square plus 2 omega c square. Okay, so these are the solution of the equations of motion for the coupled oscillators. Although our aim of this lecture is to develop the concept of normal coordinates and normal modes of vibration. Okay, but in this lecture I have not I have not given any idea of these two concepts. Only the basics have been actually derived here. Actually, in the next lecture, in consequence of this lecture, starting from this last equation number 13, you can see how the concept of normal coordinates and normal modes of vibration are developed. Okay, so I think you have understand this idea clearly. So watch this video seriously, and in consequence of this video, definitely you have to watch the second video to know the concept of normal coordinates and normal modes of vibration, which is the first concept of the theory of a small oscillation. Okay, thank you very much.